Hello friends, in this session we will see phasor diagram for a cylindrical rotor. We will see it for alternator as well as for synchronous motor. At the same time we will try to see their similarities and how are they interrelated with each other. Let us begin. Okay, so now let me have diagram for alternator on one side and diagram for synchronous motor on other side. Equivalent circuit basically, correct? Now in that equivalent circuit we know that in case of alternator what we will have, we will be having this EF, correct? This EF which is there, this is nothing but the induced voltage at no load, correct? No load induced voltage, we say excitation EMF also, correct? This is our EF. Now definitely it is going to have some armature resistance, so we have this RA, correct? And at the same time we have now got something called as excess. We have seen that already, correct? Is that right or wrong? We have seen that because this particular excess, it will be having XAL as well as XAR, correct? Both of them will be present in our excess itself. We have seen that in our previous sessions, correct? Yes. Then after that what you have here? Definitely you will be having here voltage VT, correct? And definitely here what we have, you will be having some excitation on the rotor which is called as field. So this is going to be IF current flowing. This is nothing but your field winding, correct? Similar way we will be having the same diagram in case of synchronous motor as well, which means see, it will be also having the same diagram, correct? We have seen this is going to be EF. Then what we have here is we have got this RA, then we have got this excess, correct? And at the end what we have got is VT, correct? And definitely this will be also having field because at the end of the day it is going to be same machine only, same machine will be there. It will either be operated as an alternator or a motor. Is that correct? Same things will be there. So definitely the equivalent circuit which is there, that will also be same. Let me consider this as IF current, which is the field current, and this is the field winding which is right present there on the rotor, correct? Now see here, what is the difference now? We have seen that in alternator we have seen field poles are ahead of the resultant poles, correct? Field poles are ahead of resultant poles, correct? Similarly, in case of motor, exact opposite we have seen. We have seen that field poles lag behind resultant poles. Is that correct or not? Yes. Since field poles are ahead of resultant poles, which means definitely EF is going to be ahead of, or we can say EF leads VT. Is that correct or not? Yes. This is always true in case of alternator. Whereas if you check out here, what will happen since field poles lag, so I can write that EF which is there, that always lags my resultant poles. Resultant poles in the sense we have seen that it is nothing but VT, and that too by angle of what? By angle of delta. By an angle of delta. We have already seen that previously. Is that correct? Yes, sir. Now, what changes do we have? Let us see. See, if you assume that this VT is at an angle 0 degrees, then definitely this EF which is there, since it is leading, I will write it as EF at an angle plus delta because it is leading by an angle delta. Is that correct? Yes. Similarly, in case of motor, if that this is VT at an angle 0 degrees, then definitely this is going to be what? EF at an angle minus delta. Is that correct? Yes. Minus sign, why, sir? Because it is going to lag behind, because it is lagging behind by an angle of delta. Is that correct? Yes. Then next thing is what here? Yes. Next thing is about IA, armature current. Correct? Armature current. Now, if you think of IA, in case of alternator, we have seen that they will be in the same direction. This in this voltage and I current which is there, they're in the same direction, which means this is going to come out here this way. This is going to be your IA. correct? Whereas in case of motor, what will happen? Motor IA has to come into this one, into our motor IA. Is that correct? Now, one more important thing I would like to tell you. What is that? Let us see. If you remember, we had talked about X by R ratio. Is that correct? We had talked about, yes, X by R ratio. We know that for transformer is the least. After that, we have got X by R ratio of induction machine. And after that, we have got X by R ratio of the synchronous machine. And we had seen that X by R ratio of our synchronous machine is always highest, or if you see in our existing world, if you see, it is somewhere about 10. Definitely it is always there about 10 X by R ratio, correct? Anyways, so if you check out, if my X by R ratio is more, it means that my X which is there, which is nothing but the reactance. Because see, if you think of this R, the resistance which is there, this resistance, if you check out, all of them will be approximately same in per unit, correct? Whereas, but if you think of this X which is our reactance, if you see this X will be highest in case of synchronous machines. We have seen that already. This means what? Definitely the effects of R, the effects of this resistance R can be neglected. This is the reason we can definitely neglect this RA. We can definitely neglect this RA. Is that right? We will try to neglect this array. Now, if for example this array is not there in your circuit, this array is not there, then your circuit will simply have this EF at an angle delta, VT at an angle 0, and this excess and this IA current. Similarly, in case of motor as well, you will have the same stuff. Is that correct? Per unit quantities, if you see resistances which are there, per unit way, they are going to be different. Whereas this X which is there, they are going to be that way. Correct? We have seen that already. Now, anyways, now let us try to draw the Phasor diagram for the same. If I think of again same alternator on the left, motor on the right, correct? Yes. Now let me think of that at, let us say, lagging conditions. What happens for an alternator? Let us see. Okay. Now how do I draw, sir? Let us see. See, if you check out here, this VT is at angle 0, correct? Yes. VT is at angle 0 degrees. So let me just simply have my VT here. Let me have my VT here. No problem. This becomes my VT. Correct? Yes. Now, what is next, sir? Next is, since I'm speaking in lagging conditions, if I'm saying, then let me have IA to be lagging, armature current to be lagging. So, the moment I have armature current to be lagging, let me have this IA here. This is going to be IA. Correct? Now, what happens here is, let us see. IA is lagging, correct? Now, we know that we have got this excess, correct? Now, in case of alternator, we know that this EF which is there, this EF, this will be equal to what? This drop across excess means this IA excess plus VT will be nothing but my EF. Is that correct? So, VT is already there. We actually need this IA excess, correct? So, if you want this IA excess, if this is IA, then your IA excess will be where? Definitely, it is going to be 90 degrees to this one. Like this, 90 degrees to this one, it is going to be there. So, if you see, if my IA is in this direction, then my voltage which is there, that has to lead, correct? Lead inductance. Inductance, what happens? In inductance, what happens? Voltage leads the current. You know that, correct? So, definitely my IA axis is going to be this way. This becomes my IA axis, correct? This is my IA axis. What happens next? If I add VT and IA axis, what do I get? I will get EF. So definitely this is going to be EF. Is that right? Yes. Now if you see what has happened now, yes. Now if you see what has happened, definitely this angle between this VT and this EF is going to be delta. and this angle between EF and IA is going to be psi, internal power factor angle. We have seen that internal power factor angle psi. Now you please tell me whether it is overexcited or underexcited. What it is there. Let us try to see. See what is happening. Let us see. See dear, since it is operating at lagging conditions, you please ask yourself when will my alternator operate at lagging conditions? Definitely if the load connected to it, if it is inductive dominated, if my load is lagging, which means alternator will operate at same lagging power factor only, correct? Now if my load is lagging, it means that it is going to be what? It is going to be inductive dominated load. See, we have already discussed that, but still this is my alternator and this is the load, correct? If my load is operating at, let us say, lagging power factor, then what should happen? Your alternator should also operate at lagging power factor only. Is that correct? Yes, because now if your load is operating at lagging, it means it is going to be which? Inductive dominated or not? Yes. If it is inductive dominated, which means it is going to absorb reactive power or not? Correct. So if this load is going to absorb reactive power, which means this alternator has to supply reactive power to this load. So alternator is going to deliver reactive power Q. Is that right or no? Yes. So definitely this is going to what? Deliver Q. And we have already seen that overexcited synchronous machine always deliver Q. Is that correct? Yes. So definitely this is going to be overexcited. If you don't understand why it is overexcited, let me just show you something. If you remember, whenever you have lagging conditions, in case of alternator, we always get demagnetizing armature reaction effects, which means what is going to happen? Your net flux will be reduced. Is that correct? Net flux will be reduced. Now, what happens then if your net flux is reduced, which means you have to provide extra field in order to set up the extra flux which is required. That is the reason you have to operate it at overexcited condition. We have already, seen that, discussed that, correct? Now, let us try to think of the alternator in leading conditions. In leading conditions, same thing. I'll be having VT here, correct? Let me have VT here, correct? Now, IA will be where? Definitely, if it is leading conditions, then IA has to lead my VT. So, IA will be somewhere here. Now, you please don't at all think about IA access or not, whether it will come upside or downside. Wait, I'll tell you. What will happen? See, IA access. If you see IA access, so definitely 90 degrees to IA passing through VT, there will be IA access. Now, whether it will be here or it will be here, we don't know, correct? But we know one thing, that my EF which is there, that has to always lead my VT in case of alternator. So definitely EF has to lead. So I'll be having my EF over here, which means definitely you can think of it as a shortcut as well. So definitely my E axis is going to be here. Is that correct? Is that correct or not? Yes, correct. Now, what happens next? This is lagging and leading conditions. Now, again, if you observe here, what is happening? See, if I have the alternator and this is the load connected to me, correct? If my load is leading, if my load is leading, what is going to happen? Which means it is going to be capacitive dominated load, which means it is going to supply reactive power or not? Supply reactive power, which means what will happen? My alternator has to absorb reactive power. Is that correct? So definitely here I will absorb Q, and we have seen that under excited synchronous machine always absorb Q. This is going to be under excited synchronous machine. Or else if you think of, if it is operating at leading, what is going to happen then? If my alternator is operating at leading conditions, it means what will happen? Magnetizing armature reaction effects will be there, which means flux will increase or not. Yes, that is the reason I should provide less flux, which means it will operate at under excited mode. That is what we have seen already. Now let us think of the synchronous motor. For example, at let us say leading. Let me consider leading condition first over here. Now, what is happening here? This is your VT. Now here if you see, because since you're supplying VT, now see, this is EF at an angle minus delta, which means here EF should be lagging my VT. We have seen that already, correct? Now if you check out by applying our simple mesh analysis also, you can understand that here this Vt which is there, that will be equal to my Ef and Xs. Vt plus Vt which is there, that will be equal to Ef plus Xs, or I can say that this Ef which is there, it will be nothing but equal to Vt minus Xs, Vt minus Ixs, depending on that equation, KVL equation. What I am saying is, don't think about Ixs. We know the shortcut. Shortcut is what? If it is a synchronous motor, then my EF has to lag my VT. That's it. By an angle delta. Problem solved. Correct? By the way, here also, angle between this EF and this is going to be delta, and angle between this IA and EF is going to be psi. Correct? Anyways, let us think of motor. So, let me have my VT over here. Let me have my VT over here. Correct? Yes. Now, what happens to my IA? The moment I say it is leading, which means it is going to be leading. So IA is going to be leading this way, like this. Let me have IA leading over here. Correct? Yes. Now, where will be my IA axis? Don't think about IA axis. We don't need that. Why? Because whenever we are talking about synchronous motor, it means that my EF is lagging my VT, which means definitely if you see IA axis only if you want, then definitely it will be 90 degrees to this IA, correct? Yes, now whether it should be here or here, for that we have seen that our EF which is there, that lags my VT. So if my VT is here, then definitely my EF which is there, that is going to lag. So somewhere here I will be getting my EF, and somewhere here like this I will be having my IA axis. Is that correct? Yes. Problem solved. Now again, let us think of angles. Definitely, angle between this VT and EF is going to be delta, and angle between this IA and EF is going to be psi. We have seen that interval of a triangle. Now, since your motor, if it is operating at leading conditions, what will happen? Let us see. Motor in the sense, is it your load only? Motor is the load. If it is operating at leading conditions, which means what is going to happen? It is going to have capacitive dominated or not? Yes, capacitive dominated will be there. If I say that it is going to be capacitive dominator, then it is going to supply reactive power or not? Yes, so definitely here what will happen? It is going to deliver reactive power, and we have seen that synchronous machines which are operating at overexcited conditions will always deliver reactive power. You have seen that already, correct? Anyways, forget about it. Now let us try to think of lagging conditions in case of synchronous motor. Let us see what happens now. Again, let me have my VT over here, correct? Yes. Now where will be my IA? Since it is lagging, which means IA is definitely going to be somewhere here. So let me have my IA here, correct? Now what about IA axis? Definitely 90 degrees to this is going to be IA axis this way. Now it is up or down, we do whether it is here or here, we don't know. So, but then we know that we have the shortcut. Conclusions we have. What does that say? It states that EF lags VT. It says that EF lags VT. That is what we have already seen. So if my VT is here, then definitely my EF has to be somewhere here. So let me have my EF over here, because the synchronous is very easy. Students are scared about synchronous, but it's okay. Slowly, gradually, you will understand everything. Believe me, trust me. Anyways, this is your EF, correct? Now, what happens to IA axis? Definitely, your IA axis has to be here, this way. IA axis, correct? That's a problem solved, correct? Now, what about the angles? Definitely, angle between this VT and EF is going to be delta, and this angle between VT and IA is going to be psi, correct? Very easy phasor diagrams or not? Yes, very easy phasor diagrams. Which means what the best thing is that you don't need to think of, IA axis is taken positive, negative, whether it will come up or down, slant, whatever it comes, we don't care. Why? Because we know the basics right. We know that EF always leads VT in case of alternator and EF lags VT in case of what? In case of a synchronous motor. Is that correct? Yes. Now let us think of next. Now definitely here also what will happen? Here also what will happen since it is operating at lagging. Just say if your load is operating at lagging, which means what do I say? It is going to be inductive dominated load. If it is inductive dominated load, then it is definitely going to absorb reactive power or not. Yes. So this is going to absorb Q, and we have seen that under excited synchronous machines always absorb reactive power. Correct? Already we have seen that. So yes. So if you see means by ignoring our RA, we have tried to find our Phasor diagram for alternator as well as for synchronous motor. Next video we will try to see some practical applications or practical requirements of our alternator and synchronous motor which has to be seen. Thank you.